And we will continue with our next speaker, who is Ahan, who is a member of the technical staff within the Mobile Network Systems Department at Nokia Bell Labs in Morro Hill, New Jersey. He obtained his PhD from the Georgia Institute of Technology in last year, and his current research interests include 6G network systems, open radio access networks, non-terrestrial networks, and software-defined networking. And he will talk in his presentation about ProSlice, programmable multi-red network slicing with OAI in the Open RAN area. So please welcome, Ahan.
So thanks for the thanks very much, Robert. Hi, I'm Ahan, and today I'm talking about ProSlice. So ProSlice is this multi-rat ORAN platform that we've developed on top of OAI using OAI as our base. And the key use case that I'll be talking about today is of network slicing across both 4G and 5G. And just to provide some background context, we started this work back in 2020 when the first U283 specification came out, that was U283v1. That was, of course, with the 4G OAI stack. And last year, when the 5G SA started to release by OAI uses over our platform, that was kind of both 4G LTE and 5G SA. So I'll be talking a bit about the platform architecture, and then we have a short demo towards the end, showcasing the use case that we've developed. So yeah, let's begin. So I guess everyone here is pretty familiar with the ORAN architecture, and the previous presentation, of course, also covered ORAN in depth. So I'll quickly go through the background. So now, traditionally, we've known that RANs to be this, closed monolithic black box with not much opportunity for external customization. So you have this one-size-fits-all approach, where you have a PlayStation or the DTS, whatever. The idea is that they cannot be sort of controlled externally by a third party. And that's something that ORAN set out to change. So through ORAN, now you have these three tenets of disaggregation, programmability. So you have the RU being split off from the BU, the RU and the BU, and then you also have these RAN and controllers or RICs, and ORAN releases two RICs, the near real time and the non real time. And we'll talk about that on the next slide. So the idea is that through this programmability that ORAN brings in, now you have a rich third party ecosystem that can sort of control and program your RAN for you. And as a result, we have a number of use cases that ORAN has been enabling. So network slicing is a key one. You also have infrastructure sharing, enterprise wireless, UAV networks, and so on. So, and this is a slightly more closer look at the ORAN architecture. So you have your BU and the RU, and then you have the two RICs, the non-real time and the near real time RIC, and as we know, like I'm guessing that this is a fairly familiar slide. So the BU has the RLC MAC and hi-fi, and the RU has a low-fi and R. And the interface between them is based on the BGP split, and then you have the front call that essentially links your BU to the other. Right? On the control side, you have the non-real time RIC and the near real time RIC. For the non-real time RIC perspective, okay, that operates on time scale greater than 1 second. The idea is that the non-real time RIC formulate policies that are then pushed down to the near real time RIC. And the near real time RIC that operates on time scales of 10 milliseconds or larger. And its primary aim is to interpret the policies that you receive from the non-real time RIC, as well as serve as a site for training and deployment of machine learning models. Now, all of these new components that come in through ORAN, they also need new interfaces. So you have a bunch of interfaces that ORAN introduces, and you have So you have the P2 interface that's between the near real time and the RAN. You have the A1 interface that's between the non-real time and near real time, and then you have the O1 and O2 interface that are essentially connecting your SMO to the RAN. So within this context, what we are specifically focusing on is RAN slicing, right? And RAN slicing is a key use case for the ORAN architecture. So today, if you look at the different specs released by the ORAN Alliance, that's the standardization body behind ORAN, we see a bunch of slicing related use cases such as RAN slice SLA assurance. Now, RAN slice SLA assurance essentially uses both the near real time RIC and the non real time RIC to enforce slice SLA. And then you have the NSSI resource allocation optimization use case. And this is fairly similar to a classical SON use case. I think we are looking around 15 minutes or so here. And that's being coordinated by the non-real time. And And then finally, you have a more advanced use case of RAN sharing where you have a single site with owned by a specific operator, and then you have two operators sharing the site, maybe with their own non-data. So within this context, given the key role that RAN slicing occupies within OAI, we set out to achieve a couple of objectives through this pro-slice platform. So the first thing we want to do is that we want the platform to have both monolithic as well as fully disaggregated network functions in the spirit of OAI. So on the one hand, you have your E0P or G0P. On the other hand, the platform will have a CUCP, a CUP, a DU, and R. Right? So that's like a key goal. The next thing is that okay, since slicing is like front and center within ORAN, okay, we wanted to have some sort of slice programmability, but not just for 5G SA as a spec support, but also some solutions for 4G. So this is kind of motivated by the fact that 5G SA networks are still far, like few and far between. So we have a solution that is sort of targeting slicing across both 4G and 5G SA. And then the final aspect was okay, now that you have this kind of platform, how do you sort of control it, right? So this is where the real time rate comes in. And with the real time rate, what we wanted to do was that we wanted to make it very simple to sort of perform slicing related activities, so that you don't really have to, download an X app or kind of like figure out the internal architecture of the real time, but how do you make it very simple to sort of perform slicing related activities? So that's sort of like the key objective that we set out to achieve. And in doing so, we sampled the different open source RAN stacks that exist today. And what we realized is that OpenAirInterface are really setting the standard for open source RAN solutions. And why I think that is because it presents an excellent starting point for building an OAI compliant platform of this kind, where we have these different network functions that we want to support, and also then slicing with the data and so on. So as of today, OAI supports, of course, 4G LTE, 5G LTE, and 5G SA, and then also you have some amount of disaggregation support with the CUDU split. Other key aspects that drew us towards OAI is, of course, the fantastic developer community behind it. Like you have the VP update, and a very active community on the mailing list, and there's a lot of technical discussion back and forth, and that kind of really drew us towards using OAI for our research work. And of course, beyond the community, it's probably also the most feature complete open source stack available today. You have FTD, TTD, bandwidth path, and so on. So it's pretty fairly feature rich. And also another key aspect is that okay, you have the UE stack that allows you to non-standard compliant research. So for some aspects where we want to do something that's not in the standard, it's not possible for us to use a cross UE in that case. So UE stack does that. And of course, then you have the RSTIM or emulation mode that allows for rapid development and testing. That's a bit about why we chose OAI for this work. Having set the context for that, this is sort of a preview or overview of the ProSlice platform. So I guess we'll start off with the E0P here. So at the outset, you have your E0P and C0P as the monolithic entities that exist. And then we also have CUCPs and CUUPs, and then the both for 4G LTE and 5G SA. The idea is that we want multiple CUPs to be able to connect to a single CUCP, and also have multiple DUs interfacing with the same CUCP. So essentially, your CUCP forms your control entity in the RAN, and then you have all these different user plane entities attached to it with multiple user plane CUPs and multiple DUs. And also that we wanted to have the same thing for both LTE, that's what we came up with initially, and then 5G SA something that we added to this now. On top of this, like base RAN elements, then we have the slicing framework that we've incorporated in the platform. So since we said that slicing is the key use case that we were trying to explore through this work. So we have the slicing framework, and I'll talk a bit about what the framework looks like and what the parameters and so on. And then once you have the slicing framework, to be able to interface with the real-time, you need an E2 agent and you need a service model. So I'll talk a bit about slice related service model and E2 agent within the RAN. And then once you have the RAN platform, on top of that, we have the real time. So here we're using the OSCF with certain modifications to support the slicing related use case. So a couple of things I'll talk about in that sense are the 2x app, and then a graphical front end for the real time. So that's a bit about what the platform looks like, or kind of like the big picture. Yeah, so beyond that, let's talk a bit about the RAN slicing framework. So it's intended to be a slicing framework that supports LTE and SA, I guess in principle you could also support NSA, nothing stopping us from doing that, but our evaluations and such are based on using NCE NSA. So the idea is that within this slicing framework, slicing is characterized by a number of aspects. So first is that, okay, what kind of access technology does this slice belong to? What's the state of the slice? I'll talk a bit about what slice states mean within this context. Beyond slice states, okay, we can have multiple CUP associations with the slice, and these are things that can be changed dynamically. So today, at this second, you could have a CUP associated with this slice, maybe at the next session, this CUP is no longer associated with that. It really depends upon how you want to set up your video methods and user connections and so on. Beyond that, you can have resource configuration for each slice, training algorithm per slice, and of course, also a slice characterized by the users or bearers that are associated with it. Speaking specifically about the slice state, so we have this state machine, and within this platform, slices can exist in one of four states. So a slice can be idle, a slice can be shared, a slice can be prioritized, and a slice can be dedicated. So initially, when there are no users or more specifically no radio bearers associated with the slice will be idle state. It's active in the sense that it's provisioned in the RAM, but it's idle, so it's not really doing anything. The moment you associate a bearer or a user with the slice will transition to one of three default active states. And one of these three states could be shared, prioritized, and dedicated. Let's begin with the shared state. If a slice is operating in the shared state, essentially what that means is that all slices that are shared, they're all sharing a common resource pool within the RAM, and they also share a common system level scheduling algorithm. So say if your shared algorithm is total to be round robin, all your slices will be using the round robin algorithm. Beyond shared slices, slices can be prioritized and slices can be dedicated. Now, what do you mean by a prioritized slice? Essentially, when a slice is prioritized, what we mean is that okay, if you assign a certain set of resources for this slice, these resources will be used by the slice if the slice needs them. So in some sense, it can be considered similar to preemption, where say you prioritize maybe 40 resources for this slice. If the slice ends up using all 40, fair enough, you can. If not, the unused resources go back to the shared pool. That's what the prioritized slice is about. And each prioritized slice can have its own training algorithm. So the default algorithm that we're using is a weighted version of proportional pair, but you could also have some other solutions like round robin or CPI-based algorithms. Talking about dedicated, and that's the third state or the fourth state. So dedicated slices, as the name suggests, have a dedicated resource assignment. And by dedicated, mean that even if the state RAM slice does not end up using a certain set of resources that are assigned to it, these resources will stay with that slice. Now, at the outset, this might appear a bit wasteful that if you operating a slice in a dedicated mode and it does not end up using all these resources, you might, your radio utilization will be poor in that. So the idea is that the dedicated slice is not intended as a permanent operating mode. This is more for cases where, say for example, there is a public safety event taking place. So your usual public safety slices say they were operating in the prioritized mode. You can also be dedicated to ensure that no one else can really preempt those specific slices. So that's a bit about the slashing framework, and we see we have a number of state transitions here. So of course, usually a state can transition when users are added or removed from the slide. So say all your users leave the slide goes back to idle. That's one possibility. Also using the rig, what we can do is we can force state transition. So we have a bunch of APIs for the slicing framework that allow you to sort of switch the slice state, or rather you can switch any of the RAM slice characteristics that we mentioned. You can switch, of course, not the time, you can switch the state, you can switch the users associated, you can switch the UUP association, the resource configuration, and so on. So anything that your state machine or slicing framework provides to be configured can be configured using set of APIs that ultimately interact with the E2 agent and ongoing setting. So here we have a very simple use case that very simple evaluation that showcases what's the performance impact of operating in a different state. So we have a simple case where we consider two slices. For this case, we were operating at 100 PRDs, total of 120 MB per second. So essentially, when both slices are shared, okay, they share the equal number of resources. So you see here that the throughput is the same. Then at t equals 20 seconds, we issue a rig control request from the rig that can switch the state of say slice 2 from shared to dedicated, and then you have a specific dedicated resource assignment that increases throughput. Right? And then from t equals 20, t equals 40, you have slice 2 with high throughput and slice 1 low throughput solely based on the configuration you set up. And then beyond that, P equals to 40, we see that, okay, say you stop running traffic in slice 2. Now this slice is dedicated with a decent amount of resources assigned, but it's not being used at this point because there is no traffic in this slice. However, on account of the dedicated mode of operation, essentially slice 1 is not able to use these unused resources, so they stay with slice 2 and get wasted, right? So as a result, we switch from dedicated to prioritized, and okay, once we do that, we see that, okay, any unused resource is released back to the shared pool, and slice 1 is able to sort of increase its throughput because of this, simply because of resources are available. So that's a bit about the RAN slicing framework. And the next thing is, okay, so now that you have this slicing framework, you need some sort of supporting service model. So now here I want to emphasize that when we began with what EQSM-RC and more recently EQSM-PCC, the configuration and control, they weren't really available, so to speak. So as a result, some of these parameters may be reflected in RC at this point, but then again, not everything in here is in RC anymore. Right? So we call this service model the MRSH or multi-radial slicing network. And the idea is that it kind of integrates with our RAN slicing framework that was one we had, the RAN slicing framework. And it also provides a set of RAN function APIs to sort of configure and configure the RAN, configure the slices, and collect statistics all the way up to the X. Right? So talking about statistics, what are the kind of statistics that RSH supports today? So we have three classes of event triggers. You can collect reports periodically, you can collect reports on demand. You can also track any slice related context change in the RAN. This is done to ensure that if there is any context change in the RAN that the RIC is not aware of, so this could be to some signaling from the core, or this could be maybe if you're using some sort of element management system, like you have an RNSM or a network function management function that makes changes to your RAN that the RIC traditionally would not be aware of. This kind of context change reporting will ensure that, okay, your RIC and RAN are in sync with each other insofar as RAN slicing. So given these different kinds of triggers, so you can configure both periodic and on-demand reporting for both slice and user statistics. Talking about slice statistics, of course, this is a short list of stats we support. So again, what is the CUP associated with that slice, what's the scheduler, what's the resource configuration, and then some UV related statistics like throughput latency and local occupancy, right? And this is a very much work in progress kind of situation where we have these statistics right now, but going forward as we release different variants of the service model, we'll be adding more and more statistics. So then beyond slice statistics, okay, you have user statistics. So for the user statistics, we have the access technology, and then we have this idea of UE priority. So by UE priority, what we mean is that say you're in a situation where you're an NPNO and you've been given a slice by your base network operator. Now, for whatever reason, in this slide, all the PDU sections that are set up the default 5QI for QoS as decided by the base operator. Right? So as an NPNO, you do not have much opportunity for QoS configuration insofar as your specific users are concerned because everyone is operating on the same 5QI. So here we have this kind of RAN priority where in addition to the 5QI, we also have a RAN level specification metric that allows whoever is the slice can to sort of differentiate the different users, given that they otherwise might have the same keywords. And how one uses RAN priority, now that is very dependent upon the scheduling algorithm. For example, if you're using a weighted proportional priority, you could use the RAN priority to calculate weights. That is one possibility. Beyond UE priority, then we have some other metrics like, okay, for this specific user, what was the last event that caused a change in the slide? So that's like, in case you're collecting reports, it's helpful to know that if this user has, for example, added a second PDU session, what slide does this PDU session belong? That's something that would tell you that information. And then, of course, the different slices that the user belongs to, what are their states, what's the throughput for the user, what's the latency, and then again, some other metrics such as the DBS, RLC buffer frequency, CQI, MCS, and so on. And finally, beyond statistics, then you have the configuration. So for configuration, we can configure a bunch of parameters. The slice parameters are similar to slice characteristics that we talked about previously. Beyond that, for the users, right now we only support changing RAN priority, but going forward, we might add in more metrics, especially when we consider mobility or something that we are working on right now. Insofar as the system itself is concerned, for 4G, we allow the RIC to add, remove slices, move users across slices, and so on. For the 5G case, at this point, we just allowed existing slides to be modified, as well as modifying existing user configurations, because, at least in my opinion, Adding or removing sites is probably outside the prerogative of the radio time. We can probably be coordinated with the SMO or if you have some other distributed rate management system. So that should maybe add or remove that from the line. So for 5G, we do not support adding or removing sites. So that's pretty much a design decision. There's no technical limitation in adding or removing sites for 5G as we do. Beyond that, so this is kind of the final piece of the puzzle insofar as the platform is concerned. So this is the near real-time that we have inside the Global platform. Now, this is based on the OSP or software community with certain enhancements to allow for translating. So essentially, what we've done is we added in the service model, the RSH service model, and then supporting XAPs, what we call the MRSH configuration and MRSH statistics. So essentially, these are doing what you want them to do in terms of like configuration and statistics. So for the configuration XApp, in the interest of maintaining ease of use, we have a simple REST API that allows you to perform the different configuration actions that the RSH model supports. And for the statistics XApp, you can collect the slides and use the related performance data. Also, you could use the information that's coming in from the statistics XApp to sort of maintain some sort of SLA working in tandem with the configuration XApp. And finally, the next slide, I talk a bit about the graphical front end that we have that really allows you to, instead of a one-click slide configuration and statistics approach where you just nice user interface and you can specify what's the coverage area for the slide, what's the configuration for the slides, and so on. So I'll show that. So this is essentially the graphical front end where first you have this network view where you can see where all are your grid-connected base stations in the RAN. Beyond that, you can check your network status. So what are the different again, what are the different nodes in your RAN, where are they located, how many RAN functions they have, how many devices they have, and so on. And beyond that, you have the slice station dashboard where if required, you can create and configure slices. So here you can set, okay, what's the SSP, what's the NSSAI, and so on, and what's the resource configuration in the slice, and then you can monitor the slice that you created in the slice status dashboard. And then finally, you have the slice statistics dashboard, which is essentially visualizing all the statistics that you've collected using your RSH RAN function. So that's a bit about what the front end looks like. And beyond that, now we'll showcase a demo for the ProSite platform. So the demo setup is fairly simple. We have essentially a Kubernetes cluster that is sort of called that we call the edge cloud. And then you have some sort of on-premises equipment where you have a Windows SDR, a bunch of watch series. And insofar as the demo is concerned, we run the DU, configure the RU on the Intel loop, and then everything else is running on the cloud. So we have the near real-time rate, the CCP, the UP, the core network, all that's running the edge cloud. And of course, this is just for the demonstration purposes, needed to be deployed in this manner. So through this demo, what we will showcase is first the runtime programmability of translating operation. Also, that way, like the operational flexibility that the slice state routine brings in, that's another key aspect we want to showcase. Through this demo, finally, okay, you can have some sort of fine-grained performance control by modifying the slice configuration. So now I'll get to the right. So right. So just to set the context of the demo, on the right hand side, you have two class series. On the left hand side is a Pixel 4a 5G. On the right is the OnePlus 8 5G. And right now, both have been configured for operational 5G SA only. On the left hand side, you have a core network. We're using the Open 5G as core network. The Pixel is intended to connect to slice 1, and the OnePlus is intended to connect to slice 2. And throughout this experiment or demo, slice 1 will be operating in a shared mode, and we will be changing the state of slice 2 from dedicated to prioritize and then showcasing the difference in the database. Of course, all this is being done through the MRSH configuration XApp on the link. So, I'll walk you through the demo. So, so we start off with the core network, waiting for that to come up. So now the core network is running the more the RAN. Here you have this UCP, and here you have this UUP. So we'll start off with this UCP first. And here we see the latest are successful, we see the response from the rig, and in response to that, we've activated that specific line function. Within the CUCP, also that the NG server is successful, that showcasing that. And this is like a debug of the equality message that the equality response from the rig. Now we start the CUP. Similar stuff, first we establish the even interface between the CUCP and the CUP. Now that CUCP and CUP are connected. And then also the CUP interfaces with the link. You have the that are successful and you activate equal message at the CUP also. Next we will go to the DU. So this is like the DU configuration file. A slightly modified version of the regular OAI DU configuration file where we are able to add in the slice list that we want. Here we have slides on, as I said, this is the shared mode and slides to have to be dedicated. Now we start off the DU. And the F1 with the CUCP that part second. And under the DU is transferring on air. We go ahead and disengage airplane mode for UV1, which is SSD1 in the shared mode. Okay, the PD message established the party logo lights up. Here we see that the state of slice 1 is now changed from idle to shared. So it's indicating that a bearer has been set up for this state slice. And we also do the same for second view, which was slice 2, it's operating the dedicated mode. Now, initially, I want to emphasize that the dedicated configuration is only 20% of the resources, whereas the remaining 80% is shared slice by default. So when we see that the mode is from idle to dedicated for slice 2. And the slide second user also attached. So now that both users are attached, we can begin some sort of throughput testing to iPod. So the idea is that since this user has dedicated 20% resources and these are the remaining 80%, the throughput for this slide should be higher. And tomorrow it was about 70 to 80 MB, and this should be about 15 to 20. That's what we see here. So when we perform the throughput test, the throughput for this user is limited to 15 to 20 MB on account of resources being listed. And we see that okay, the session for the first user is over, and we just wait for the bit for the second user session to finish before we move on to the next part of the picture. Here we see okay, the dedicated configuration of only 20% of the resources. This had about 50 to 20, and we will start remaining 70. Okay, now next thing we do that we dynamic control request that changes the allocation to 53, so that's about half the RV present in the network, right? So now this has 50% of the resources are dedicated, the remaining 50 goes to this one is shared. So now the idea is that okay, since there are only one user in each side, you should have equal throughput across both. And again, these are normally backward sessions, and then check the throughput on each of these users. Yep. So we see that the data transfer starts, and for what I call is about 45 to 50 MB for each user. So this one is the dedicated one, but then again, this only 50% of the resources is dedicated. We see that the throughput is more or less the same across both users. Yeah, and then we wait to the hard confirmation mode, should be finishing up shortly. Right, so now here the high confirmation, and then we see similar level of throughput across both users. Due to, although the state is different, since there is only one user in each line, effectively it's equation. Now, next thing we do is that we only send downlink traffic for this user and no traffic for this user. Now, because this slice is dedicated, so although this slice is not using any resources, the shared slice is not able to get the unused resources because this is a dedicated mode. There's some sort of resource wastage here. You still see that this slice will be able to achieve 50 instead of requiring 100 because the unused resources are getting wasted since they're occupied by this dedicated service too. Here we see we are expecting about 90 to 100, but it's still end up being 50 because the resources are long. Okay. So, right, so next next thing we do that, okay, we don't want this kind of resource wastage to occur all the time, so we'll switch the mode of slice through from dedicated to prioritize. So we send the request code request and switch the state, the state machine to this slice to prioritize mode. Now we'll again do an iPod for the same download super, and this time we see that okay, this user is able to sort of saturate the available resource, and we see a 2,100 to be able to define to 100, right? And yeah, that will just again I can have it on the questions.
Nice question. So the near RPD, is that open source?
Yeah, it's from the OAI software community, the OSC. So they have a reference based solution. I think at this point it's a release F and it's fairly stable. We should be able to use it without much modification.
Thank you. And the OpenAirInterface, how much of modification are you need to do, and is that available as an open source?
So we are working on getting open source registration, but we're trying to get the approvals through, but maybe in about month or so it can be out.
What is and what can be open source?
Yeah, we're working on getting open source. Yes.
Thank you.
Thank you, wonderful presentation. Just wanted to understand, how is this different from the standard available slicing? Like what capabilities and differences are needed? Just the picture.
Sure. So from a standard perspective, from what I know, mostly a standard focus on the NRM or network resource model, where different resources are characterized with different capabilities and resources can be shared, prioritized, or dedicated. This kind of extends this the slice level. So now you have the slice state machine, which is sort of non-standard. So that additional resource configuration flexibility what we try to do beyond the standard. So also the CU peer association, that's not something the standard is not talking about today. So some sort of more flexibility and configuration we try to bring. Okay, sure.
Yeah, something about I just want to know these students that we are
Yeah, I do. Yeah.
So I use any virtualization like platform for like sliders, and another question is how what is the maximum of the slices?
Sure. So to answer the first question, from a platform architecture perspective, there's nothing apart from what regular OAI needs. It's just the usual x86 based CPU, and that's what there's no additional virtualization going on there. As for the second part, how many slices you could add? I mean, I would say practically unlimited, but you're also limited by how much reports you have and what makes sense. So you could have 100 slices, but if each slice only has 100, we probably not have anything that's optimized. So, yeah, it just depends on how many resources you have.
In your system design,
Yeah.
you actually have to change the max schedule to support a slide, or you have to then plan instances, with the separate scheduler, but you still have to share the spectrum.
Sure. So the RAM instance is the same. The schedulers are different and the spectrum is shared. So to talk a bit in more detail, the OAI has this nice structure in the map here where you have a pre-processor and a post-processor. The pre-processor is essentially where you take the scheduling. And with slight modifications, you can have it support different scheduling algorithms at the same time. It's definitely doable in a single time. Yeah, so slice size, so you recognize the slice and have the signaling over all your relevant interfaces.
It looks like there are no more questions. So
Thank you.
thank you, Ahan.